I think we all have the understanding of what computation is. The lambda calculus is a formal system for expressing the notion of computation. It is based on some notions such as abstractions, applications, variable binding, and substitutions. Lambda calculus can be used to simulate any Turing machine. So, the lambda calculus is a formal language, and it must have some alphabet and some syntax. Okay, the syntax of the lambda calculus can be defined using three inductive rules. And we can say that this syntax defined to us a valid lambda terms. So all the terms that can be constructed using these three rules are valid lambda terms. And the rule number one, if they have some variable, the variable itself is a valid lambda term. Okay, all the variables are valid lambda terms. Rule number two, if t is a lambda term and x is a variable, when we can say that this thing is also a lambda term, and this thing called an abstraction. Actually, it represents some anonymous function, the only one argument. And rule number three, if t and s are lambda terms, then we can say that this thing is a lambda term, and this thing is called application. Actually, this thing represents the application of the function to some argument. Nothing else is lambda term. So, the lambda term is valid if and only if it can be obtained by repeating application of these three rules. In lambda calculus, there is no concept of a variable declarations. If you're familiar with, of course, you're familiar with some imperative languages, you always define the variables there. But in the lambda calculus, there is no such a thing. All you have there some arguments which anonymous lambda function receive. And for example, here you can see this lambda term, which is actually equivalent to this function, which take one argument x, and this argument x is actually a bind variable here. And this y here is free variable because it is not defined as an argument of the function. So it has no binding here. It's defined somewhere in the context. In the lambda calculus, the function is a first-class value. This means that you can put some function into another function, and this function can again return to you some new functions and so on. For example, with this simple term, you can define the function composition, which take two functions f and g and some variable x, and then we do the application to g of this x, and the result, we put the result of this application into the f. And this simple thing represents to us the function composition. There exists a notion of alpha equivalence in lambda calculus. Actually, this is equivalence, in which we say that the two terms, lambda terms, are equivalent if they can rename the variable under a lambda abstraction and receive the same term. So we take some bind variable, rename it, and if they receive some term which actually the same as the term we want to as the second term. So we take one first term, replace the bind variable there, and they receive some term, and this term is equal to the second term, then they say that the first term and the second term is equivalent. For example, here they have this two lambda terms, and actually all they represent the identity function, because they can simply change this bind variable here, x to y, and they will have the same terms. Also, there is a notion of beta reduction in lambda calculus. Actually, this is the main thing that represent the computation step. What we do, they just do the substitution of the bind variable with some another term, and everywhere in the lambda expression body they do the substitution of this variable, and after this we just remove the abstraction path before the dot. So for example, this part, if they replace the x here with some term s, we just removed everything before this point and replace everything in t. Every x inside t we replace the s, and this is actually the one step of computation. And the lambda calculus may be seen as a idealized version of function programming languages. If they take such a language like Haskell or standard ML under the cover, it has actually the lambda calculus inside, some form of lambda calculus. And actually on every step of computation it do such substitutions. Okay, it do this beta reduction steps, step by step, and at some point it can do any steps, and at this moment they say that a computation is done. Okay, the program is finished, or function actually compute its value. Of course, there exists some situation where the computation never stop. So in this way, the reduction step can be done infinitely times, and this corresponds to a situation then our computer hanging, and actually I think we must avoid such situations. We want to avoid them. And this thing of lambda calculus, which we review in this video, is called untyped lambda calculus. There is no notion of the type in this lambda calculus. And this means that this lambda calculus have no distinguish between different kinds of data, and this means that, for example, if you write a function which operates on numbers, and untyped lambda calculus doesn't stop you that from the situation in which you put not numbers in this function, and maybe some lists or strings and so on. So we say that we can reduce the beta reduction step some terms, and the term which can be reduced is called regex. And on the other hand, when they do all the reduction steps and we can't do any more steps, this term is called reduct, and actually this is the final point of the computation. The notion of new reduction in the lambda calculus. Okay, this new reduction actually makes these two terms, for example, this term and this term equal, because they equal in the computational meaning. If they apply something to the first and the second term, we will receive the same result. And as I said, there is no notion of a variable in the lambda calculus. Actually, there is no distinguish between the actually code and data in lambda calculus. All is a lambda terms, and actually the data itself represented as a lambda terms. For example, here you have see the church numerals of encoding the numbers in a lambda calculus. In just some simple way, we encode numbers as a number of application of some function to some argument. And of course, this f and this argument x is also the lambda term, so everything is lambda term. Some terms in lambda calculus which have no free variables, only bound variables, are called, these terms called combinators. And here you can see some standard combinators, identity combinator, SK combinators, and so on. Lambda calculus and parallelism. Interesting that lambda terms has no can be evaluated in the different orders. Actually, order doesn't matter, and we can even do these evaluations or their better reductions in the parallel. So actually, this computation can be implicitly parallelized. Interesting that also exist some formal systems such as process calculi, that can describe the communication and concurrency. And the lambda calculus doesn't not offer any explicit construct for parallelism. There are many variations and extensions of the lambda calculus. Actually, there exists some notion of the lambda cube. There somehow this all different types of the lambda calculus represent in a visual form. And for example, there exists a type lambda calculus. So we add the types to variables and functions, and also exists system F, lambda calculus with type variables, calculus of construction, calculus where the types are first class values, and whereas exist some formal systems that variants of the lambda calculus which are not in the lambda cube. For example, you can see all this list here. And there are many related notions here. Okay.